Zoom. Yeah.
It says live streaming is starting soon.
It's coming up? Oh no.
Not yet.
Let me go to the thing. Live streaming. Okay, it's streaming.
Okay, let's see.
No?
So yeah, I still see live stream is starting soon.
Okay.
I could definitely see you tested it earlier.
It's not 3 p.m.
Well, 2 hours ago you did. Yeah, it says it's starting at 3.
The day is correct, right?
Yep. October 13th. Let's see.
It's streaming.
There it is. Yep.
Oh, this right here. Mine doesn't show.
Okay. Yeah, I can see.
It's moving.
Yep. Let's see. But can we hear anything? Not yet. So there should be horrible feedback if it works. Is that my speaker on?
Is it on?
Oh, it's delayed.
Why did I actually increase?
Okay, yeah, I can hear it, but
Okay.
it's really quiet.
So the pickup is not that great, right?
Yeah.
You have to speak louder?
Let's see. Try again. Why is it doing that? Yeah, the speakers on here are pretty good.
No?
But the pickup is really quiet.
So it's pretty quiet.
Let's see.
Is it mute?
Not mute. I don't know what this will do. Okay, let's see if we can hear someone talking now. We'll find out in a minute. University of Hawaii live stream. Nope.
It's not really focusing.
Yeah, I think it's too quiet because my computer can be pretty loud. But that's maximum volume. Oh my god, I can't believe somebody's watching this. Oh, it's probably you. Are you watching?
Yeah, I'm watching it.
Oh, thank god. Okay, so we could try the YouTube extender, or we could try the other microphone.
Oh, we can try the webcam stuff.
Well, that's better. Oh, that's you talking.
Let's try the notebook.
Is that the webcam?
I think everything.
Yeah, where's the microphone now?
I turn all three on.
Where's the microphone now? I think that's better.
The microphone is this one, and that one.
3 microphones.
Yeah.
It's causing some like interference though.
That's why we don't watch it here.
Yeah, that's true.
Double check the focus. I think the focus is okay though, yeah? Yeah.
I think it looks good.
Yeah, I think it looks okay. Okay.
Okay, well, we'll see how it goes. It's working at least.
Yeah, you want to come in? Let me show you some stuff.
We're gonna live stream it on YouTube. Well, it is live streaming. That's like an experiment.
Okay, why not you have 3 mic? 1, 2, and 3.
Okay.
You can do it if you want. So you can, when the thing starts, you can do a start recording. So I can never copy on my computer.
Okay, that's good.
And when you watching the thing, where are you on 720p?
I don't know. I don't think so, but
Yeah, that's cool. Okay.
yeah, it's weird the way it does that, huh?
Okay, we click on.
But it works. If you click on this, then it works.
Oh, okay.
But that's weird the way it does that, huh?
No, I think you probably have to click it. Like you can go here sometimes. Okay, we click on. Yeah, the quality is.
But it works better. If you click on this, then it works.
Oh, okay.
But that's weird the way it does that.
Okay, no, I think you. So let me close my program. And this is control panel. Basically, you can see the health
Okay.
of the stream, you know.
That's good.
Yeah, and then
Stream now beta.
it's about that.
Alright, that's good.
Just do start recording and then we will take a copy. And if you need to change any settings, right, by stream output,
I have
you can change the
terrible
bit
news.
rate.
I've lost the colloquium bell.
Uh-oh. We're doomed.
So,
Fired.
so 3,000.
Yes, please.
Let's put on the 720 is up out there.
Okay,
Please, please.
Okay. And I guess even if it's stopping, you can stop it for now. If you want to stream.
Can't go around the
And maybe just leave it on.
colloquium bell.
And we can swim all this, right? Like, suppose we want to use
I
it right
left
now.
it in here last time.
Yeah. It's a little bit high. You have to adjust.
Yeah, I see.
It's such a funny thing these days. Camera, big heavy camera tripod and the camera the size of a matchbook. Jacky, thank you for setting up. I clicked on it up in my room and it actually is there.
Did it sound okay?
Oh, I didn't hear sound. It was
Okay.
just blank when it was.
There is sound, but we're testing it in here, so it's like,
Okay. How was the sound picked up? Oh, with that?
Why not have 3 mics on?
we need a couple different microphones.
Huh.
So let's see how that works.
So, this is the camera and microphone from our lab?
Yeah, that's your
Yeah.
camera. So
Good, good.
so one is on 720p. I mean 720 HD. So you can change on the stream.
Okay, well, we'll have to see how it works out. I sent out a notice with the address, so we'll see if we have any customers. Sorry, customers, you can't talk back. Ha-ha.
Suckers.
Actually, they can lock in and chat on it. Is it chat?
Oh, really?
Yeah.
Let's not try that. I'll send emails. That's the price they had to pay for not showing.
All right.
How'd your talk go up at IFA?
Oh, I set them on fire.
I bet.
No,
Several of them went out and self-immolated.
they did. It was that exciting. They took me to lunch, can you believe that?
No, well, that's where you get out of cities.
I wonder, like, the compiler.
Is that what happened?
Yep.
Probably need to refer any changes you made trying to fix it, already updated.
Yeah. I think I might just reinstall some. And then reinstall. And it's a little work, but it means better than putting it off. It'd be
All right, how's your?
Let's see, you got the projector on. So, select you. Should run up here for a second. There you go. That'll be $5 enough.
Okay. That's all over.
That occurs.
Welcome to our side.
Yeah, we have a more beautiful exchange now between the two sides.
Yeah, we're live streaming on YouTube.
Oh, wow.
Yeah, it's a new experiment today. See how it goes.
sure about the spelling of that word. I know, should it be repellor?
Well,
Did you consult with the OED about this?
well, spell checker accepts this.
It did. Das Kapital.
It's not a repellent.
2 more minutes, Chris.
This is as good as The Great Escape with Stephen Quick.
Oh, yes. And in fact, it did get delivered up at the
Yeah.
But unfortunately, folks at IFA now know that it's on YouTube, so they can be lazy. Ryan, do you know, can we see a posteriori how many people actually watch it on YouTube?
I don't know.
It would be kind of fun to
I think you can see, yeah.
see how many customers.
That's fair. You can always take some money.
Yeah, there's a thought.
The video of my maintenance ladder. House on YouTube. 2 hits.
2 hits.
Too many of them out there. You need enough.
There's one last.
So, start the introduction, but first the coming attractions for next week, especially it would be good for faculty to be here, but also everybody else. Artis is going to give a talk about the, wait a minute, am I right? Did I get the dates mixed up? Yeah. Artis is going to give a talk about the free electron laser system here. As you know, we are undergoing a review to decide what to do after the demise of John Mady. There's a fancy committee coming here to give us advice about what to try to do. And so certainly, at the very least, the faculty will be asked their opinions on the subject. Most of us really don't know what goes on or has gone on in the FEL neighborhood, and so it's your chance to ask Artis and Eric and company what's going on with the FEL. So this week we're pleased to have one of my oldest friends at UH, Brent Tully, the man who shrank the universe by a factor of 8, something like that, or since I first knew him, because he first had a Hubble constant that was very much larger than it is nowadays, and is heavily involved in the controversy about the Hubble constant, which you should all stay tuned for, because it's significantly different from his measurements and from other measurements, and seems to be a problem. But Brent is well known, but any of you who took astronomy know about the Tully-Fisher relation. That's the Tully of SED, and many other things. I think he's probably the best known astronomer in Hawaii, and he keeps coming back and buying us beers because he won another prize, which he got about half a dozen of the last couple of years. So we're very pleased to have our good friend and scientist who continues to do interesting things even as we get a little older. And so give you Brent.
Thanks, John. Okay, good to be here. So here's my collaborators on this effort, Yoda Hoffman, Danielle Conrad, and then Courtois. So one of the bedrock bits of information in astronomy comes from a microwave background. Now, the microwave background actually has three interesting levels of information. At the very first level, you know that everywhere you look in the sky, it's about 2.7 degrees, and this is a residual from the hot Big Bang. At 1 part in 100, if you parse that down, you find that there's this dipole in the temperature map. It's hotter in one direction and colder in the other direction, and the inference is that we're going somewhere, and this is so we have a Doppler shift with respect to this reference frame of microwave background. This is a picture of that. This is a little residue of our Milky Way here. This is galactic coordinates here. If you look at 1 part in 10 to the 5, then you see that it broke out into all this mottliness, that little hot and cold spots that are in fact presumed to be the precursors of structure in the universe. Okay, that's not my story for today, nor is the first level, the 2.7 degrees. I'm interested today in this middle level of the dipole. And as I say, this is absolutely is really solid evidence that we have a boat motion then. And the question for the day then is why?
Brent, can I ask a little question? When it first got discovered, it was the 3 degree Kelvin background radiation.
Yeah.
And I think it was 3.1, but now it's down to
2.7.
2.7. How did that come?
I don't know about this 3.1. I think 3 was just a rounding.
Doesn't, okay.
Yeah. Yeah.
First order, it's 3.
Yeah. Yeah. Okay. Now, okay, so this is, anyway, what I'll be talking to you today is about a paper that this little group down here has submitted to Nature. We got some pushback on this name GRADE. You might know that there's a great attractor, there's a great wall. In the course of time, it's turned out that the great attractor is not the greatest thing around, nor is the great wall the greatest wall around. And we're being a little bit, I don't know. So anyways, there was this pushback on this great business, and so I think that in fact we're going to be calling it the dipole.
That's boring. You should have the humongous repeller.
Yeah. Because whether or not it's great in the sense that we think we found actually a greater repeller than the great repeller, and Ishvan will be interested in this down the road. But anyways, that's a story for another time. The dipole repeller then is what we should call this, namely an important aspect in this whole business of what's causing our motion. Okay, so the game that I played then with group here, Aside Quirky is here in the audience, and these are my other players here. We measure the peculiar velocities of galaxies. So the first approximation, galaxies are expanding with the Hubble law that we've known about for 80 years. We can observe velocities very well spectroscopically. And if we measure their distances and infer some mean Hubble constant for a sample, then we can anticipate what their expansion velocity should be, take that off the observed velocity, and we're left with this peculiar velocity. So that's what I do for business mostly these days. It is to be remembered, though, that the errors in this quantity here project right back into the peculiar velocities. And so as you go up to large distances, these errors get pretty big. The errors in the peculiar velocities get pretty big. And so we have a situation that after we've done all our modeling, we really have very detailed maps nearby. And it's really getting quite beautiful, actually. But our information degrades with distance.
Define nearby.
Well, 10 megaparsecs, we have shared distances and information. And then it sort of falls off a cliff. And where we're talking about here, the problem that I'll be talking about today is at the extremities of our data. Okay. Anyways, we have been collecting this data, and we came up with a Cosmic Flows 2 data set of 8,000 distances with all these different methodologies. And recently we came out with Cosmic Flows 3. We're up to 18,000 distances with these additions here. But it is to be said that everything I'll be talking about today is basically with Cosmic Flows 2 data. This was an analysis we've already done with Cosmic Flows 2. We confirm this structure that I'll talk about in Cosmic Flows 3, but the data is actually going to be using Cosmic Flows 2. Okay, so we're actually going someplace because of a whole bunch of different influences. Amongst those influences, I'm sure at some level, are neutrinos. I say that so I can get my bicycle back. And it's not registered right. Anyways, there's, for example, we're going around the sun here at 30 kilometers per second. With respect to the nearby stars, we're moving around at 16 kilometers per second. We're rotating within our Milky Way galaxy here at about 240 kilometers per second. And then we're falling towards the Andromeda galaxy at about 100 kilometers per second. Okay, these are local things that are happening. And once we take all those things into account, we can see that the local group, including Milky Way and Andromeda, we're going somewhere in the 630 kilometers per second. So that's what we are trying to explain. What's causing 630 kilometers per second motion? Well, some of that is local. For example, here's a reconstruction that we did of the galaxies in our local group. This is the Virgo cluster here. This is, the white things here are our own galaxy and Messier 31, and all of these other things are companions to our own galaxy. Here's us coming in here, and here's M31, and in 5 billion years, they're going to bump into each other. It's going to be a big mess, so stick around for that. So, okay, so we have very detailed information locally. And this is actually work I'm doing with Ed Shea, next student, colleague that I worked with for many years. And we did these orbit reconstructions. And this is another story, but it turns out that these objects, all our companion galaxies, are lying in planes, and this is a curious thing. Anyways, the basic thing here is we're all swooping down here towards the Virgo cluster, and this is a little odd.
There were some of these things almost were going back 180 degrees.
What's that?
In these pictures that you were showing, some of them were going back almost 180 degrees. What the hell is that?
Well, I'm not sure what you're talking about, but it's a little bit.
Run the film again, yeah.
Some were turning around and coming back.
Well,
No, those are the key, but they were going like.
well, it just depends on the angles anyways. I mean, these are physical orbits anyway. They all obey Newton's laws, so it's a funny, depending on.
So it's perspective?
Yeah, because we keep rotating the thing. Yeah.
But some can get flung out. It's perfectly.
Well, it could, but not any of these. None of these. Flung out. And then on a larger scale, here's the same thing, but here's the Virgo cluster, and so. Oh, yeah. Anyway, so on this scale, we have a lot of real good information, and the upshot of all of this is is to show you that, just, here's the upshot of this local stuff. Here's the Virgo cluster, each of these are galaxies here. Here's our local region here. And we're following towards the Virgo cluster. And we're in an expansion of this whole unit here. It's an expansion away from the local void. And the net result is a vector like this. Each of these components are about 230 kilometers per second. So if we take this off, this is part of the of our vector there. We take this off though, and we're still left with 450 kilometers per second. Okay, so this is what we need to explain, and this is large scale. This is all pretty local stuff. This is, this is 17 megaparsecs for you use light years. It's 50 million light years. It's still local stuff. And this is the area where we really have really great information. But we've got to explain now this 450 kilometers per second. Okay, this is something that's been, people have studied for quite a while. Here's some maps that people generated about 20 years ago of a Scheidegger and people using a potent technology. And they already saw a lot of what we will see today. Here we are here, easily identified. And we're moving, so there's these little arrows here that are showing these flow. So they had already at that time, they had velocity, peculiar velocity information. They were able to generate these maps. And here's something here that was called the great attraction. Back here is something called the Shapley concentration. Up here is something called Perseus-Pisces fault. And then you can see that there are these empty regions around here. So this already was known 20 years ago. It's quite, we don't, in the basic, in the fundamental things that we see in this map here, we don't really dispute. Here's Hélène Courtois, and this is one of our little maps here, reconstructed with our Wiener filtering, which I'll get into just a little bit more. And here we are here. You can tell because we got little arrow vector points here. There are Virgo clusters here. So that whole region I was talking about before, of the flows before, that was this little area right in here. Okay. And now here we are flowing across to something called the great attractor, and working back here is something called the Shapley concentration. So here, so we've known about this, and then now we invented this thing. Okay, how did we get all of this stuff? In the linear domain, okay, it's one thing if we're reconstructing those orbits, that's a different story. But in the large scale here, we use something called a Wiener filter, and it's a Bayesian thing here with a power spectrum given by the microwave background people, and an assumption of initial Gaussian fluctuations. Let's see. Oops. Nope. Nope. I didn't quite finish this. Okay. Okay, we assume a power spectrum. We do constrained realizations, which is to say we can run, we can try different realizations of the power spectrum, and we're left with a situation where if we've got really good data like we do locally, then the data constrains the model. But at large distances where the data becomes poor, we essentially go over to the mean density. Here's a few little issues with regard to what we do then. So we're working with velocities, and so the linear regime that we're assuming here is pretty good down to a few megaparsecs. This is an important point for what I'll be talking about today. There's great coherence in flows, and they're responding to very large scale features, and so we can actually have some information about things that are even beyond where we have data because of convergence in flows. And so we can actually see tidal effects beyond where we actually are making measurements of data. This is a really spectacular aspect of this Wiener filtering, and it's and we've really demonstrated it as we've gone out, as we've started with looking just within 3,000 kilometers per second, but seeing tidal influences at 5,000 or 6,000, as we've gone in out with data that trickles off at 10,000, dribbling up to 15,000, seeing influences at the extremities of the data. We can play a game of separating flows that are local and tidal. So we can find global flows with our Wiener filtering, and then parse it down such that using this Poisson equation here in the cosmological context, where the coefficients here actually depend slightly on the model, the cosmological model. But you've got this relationship between density fluctuations and the divergence of the velocity field. But we can then separate out local effects from tidal effects. Okay, that'll be something of interest. And then finally, just as one of our tools that I can talk about, we can talk about the V-web, the velocity web, where we look at local shears in the velocity field. So we're looking at local shears in velocity in 3 dimensions. And if we've got inflow on all 3 cardinal axes, we're talking about a knot. If we've got outflow on all 3 cardinal axes, we're talking about a void. And filaments and sheets are in between. And I'll be showing you some pictures like right here. Oops, not quite here, but pretty soon of filaments and knots. So anyways, here was this Laniakea business that we got some fame over. The Laniakea then is a region of a basin of attraction, where if you're within that basin of attraction, all the flows are going towards this great attractor region. Now, it has to be said that this is a local basin of attraction. The fact is that, in fact, so up here is this monster Shapley concentration. The fact is that there's actually a flow across this whole domain here. And that on a large scale, Laniakea is flowing towards Shapley. And then, but locally, you've got these flows in here, and we call that the Laniakea supercluster. Okay, here's a 3-dimensional view of Laniakea with some of these things lying around. And here's the V-web. So here, down here you see knots. These are places where the eigenvalues are all positive, and eigenvalues of the velocity shear are all positive, such that we can infer inflows in these regions. These are filaments where you've got collapse on 2 dimensions and expansion on another dimension. And it's, both of these maps are the same here. These flow patterns here, these are the large scale flows this is just with seeds in certain strategic places here, but we put down the seeds and see where the flows would be if you were sitting there, and we find then that seeds in this area here would come and end up over here at the Shapley concentration. The colors represent acceleration and deceleration. So you're accelerating into knots and then coasting through the knots and decelerating and accelerating again. Okay, a fine point. But wherever we put seeds here, they're ending up over here at Shapley. Now, if we take out the tidal component and just look at local flows, then we see that there's these little local flows in towards the various knots, and give them various names here. And remember that Lania Kea features is buried in here. It's like some sort of biology.
Pelvis.
Pelvis is pelvis. So, that takes me to movie. So we made this movie. And I'll just talk along with it here. So here's the filaments and dots of the V-web. This is the 630 kilometers per second motion of the vector of the microwave background dipole. This is us up, okay, here we are down here in the center. And as I say, we're going somewhere down here. And you can see that it's vaguely in the direction of Shapley and Great Attractor, but not quite. It misses those things by 20 degrees or so, and that's been well known for a long time, that our motion is vaguely towards those guys, but not spot on, okay? The dimensions we're talking about here is a tenth the velocity of light. That was 0.1 c across there. So here we put down a whole bunch of seeds and asked where the velocity flows would go from those seeds, and they end up coming around here to Shapley. The next thing we did though, and let's see, okay, we'll do a little rotation
But this
here.
is, when you put the seeds in, you assume nothing outside, or? what?
Well, we just put seeds all over the box, and then say, where would you go?
But what about the stuff outside, gravity from an outside box?
Well, we're not seeding now.
You're assuming no tidal influence?
Well, there could be, but that we're not seeing, well, okay. What we've done here, just to keep up with my movie,
Oh, sorry.
yeah, is we just reverse gravity. And so these red, yellow things are where you would go if you flip gravity upside down. So the top, you're now going to empty places from dense places to empty places. And that's what the yellow red is. So we've now got here in blue, positive gravity, and in red and yellow is inverse negative gravity, if you like, going to from seeding and watching the seeds go to the lowest density place. And that's what we're calling the great repeller, because everything goes to that one place. And here's the form of Lania Kea in there. And we're now going to go around. Here's this vector here for the dipole motion. And I think that about now we'll rotate around and see, looking down the throat of that direction, and you're seeing we're lined up here with this great propeller. We're going to go around the other side where you can see it even better. Here we are looking down the vector, and back behind there is the great propeller. And you can see that the great Shapley is up here, the great attractor is over there a little bit off. So our assertion then, this is the assertion I'm going to make, and it's the conclusion of all of this, is that in fact the great repeller is a very important component that in giving rise to this motion here. Shapley plays a role, great attractor plays a role, great repeller plays a very important role. Probably of roughly equal amounts. But it's the great repeller that's very much aligned then with this vector. And remember that the vector came from totally different information, right? That's totally different information. So that's my story. And this is one of your shorter colloquia. But
Okay. Shall we applaud now? or
yes.
Why is the repeller not an attractor?
Yeah. Well,
Why is it a repeller?
why is it a
not an
repeller? Well, it's a repeller because there's nothing there. That's simply that. I mean, it's, if you have a uniform density of stuff, but you just carve out a hole that hole will be expanded just because of the lack of stuff there. And that's what voids do. And that's, for example, in that early stage when I was talking about way back in this early stage here, the local void is pushing us at 230 kilometers per second. That's a very local effect, and it's absolutely certain that this is happening. Yeah. What's that? I'm not sure what's the question. I don't. Yeah. Yeah. Well, this not the status of this 600. Oh, it's really, really accurately known. Like the error bars are a couple of kilometers per second, the directions a couple of degrees. Yeah. Yeah.
You're
This
just
is
talking about the cosmic flow, not our flow, but the other flows that are.
the what?
Dark flows.
Dark flows. Later.
They have fun.
What do you refer to in the dark flow?
Dark energy? No. At least people don't talk about it.
Well, what is that?
Kashinsky came up with a paper a few years ago
Oh.
about this dark flows.
The dark, the Kashlinsky thing. Well, yeah, I can comment on that one, but, you know, that's plausibly what would be an important thing here. And the claim.
What he's talking about, dark matter flowing, that's,
Here, the claim is that this flow of 630 kilometers per second, we're trying to explain here, or 450 here anyway, is on a scale that's beyond anything I'm talking about here. That is, the evidence is coming from the kinematic Sanyaya-Snelldovich effect. And the evidence is that the claim is that clusters on scales of 0.3 C are participating in this. It's disputed. Nobody else agrees with this. A bunch of other people, nobody else agrees with it. But the claim would be then that this bulk flow isn't constrained to this local dimension, that it's actually going on to a very large scale. It's exponential. So if it was, this would be contradictory to the lambda CDM model. The lambda CDM model accepts that you could have flows on this kind of a scale going up to approaching 0.1 C. Well, approaching that, and still you could say that's okay within lambda CDM. But if you're getting up to 0.3, that would be too big. So Kashlinsky's thought is, just the thought, well, what would it be? He's arguing maybe it's mass beyond the horizon. Okay. So that's part of this game. I'm saying, or we're saying, that probably all the explanation's right here. And a lot of people looking at the KSC effect saying, we don't believe what Kashlinsky thinks. So that's
what is the explanation that's right here?
right here?
Yeah.
That there's pullers and pushers, but that the great repeller is a significant part of it. And in fact, we're arguing that the very interesting aspect of this is this alignment, that it's so nicely aligned that we can probably infer that this is a significant contributor. That's
But you
pushing.
don't need my old favorite of repulsive gravity mirror matter in the hole.
Yes, well, of course, you can, that could be an added thing if you wanted, but we're just, well, we don't know the amplitudes very well because it's at the edge of our data. So, we wouldn't want to say that we need anything else except just an absence of gravity there.
Just one more question along that line, but you used to tell me over beer that near the edge of the, our nearest void at any rate, the galaxies were moving too fast for the calculational lambda CDM. They're leaving the scene for sure,
Yeah.
but that their velocities were too high to understand from the
Well, this is,
digital simulation.
we have a model for this flow that I just showed you here. And the fact is, we've actually got a nice object up here. And the fact is that it has a velocity that's about the best part of 100 kilometers per second, larger than our model would like 80 kilometers per second. It's like a 2 sigma thing, we're not sure if that. And also the other thing is, we've got a misfit on the velocity of Virgo by about 100 kilometers per second. There's some small hidden details there.
100 kilometers per second, all friends.
When you say 450 kilometers remains unexplained, I mean, what would the vector, my understanding is the yellow vector is basically our local void plus Virgo.
Yeah.
What does the real vector look like?
It's pointed into the, yeah, so the great attractor and the rest of the vector is almost,
Perpendicular to
yeah,
the
yeah,
to the plane. Okay.
yeah.
It's fun.
So presumably the great repeller is actually a void.
Yeah.
So you don't call it that, but how big would that be and how deep?
Well, of course, it doesn't have to be just a single void. It's just an underdense, general underdense region. It probably has filaments and things. It's probably messy. And it would be big. It would be, I'm gonna say 8,000 kilometers per second or something across, 10,000. It's the general empty area. You know, of course, the obvious thing to ask is, well, what's going on in that area? The fact is that it is underdense, but it's poorly explored. It turns out to be rather close to the zone of obscuration. It's big enough that it spills outside the zone of obscuration, but it happens to be in the direction that's least surveyed by redshift surveys. For those who are not in this field, so there's been some really big redshift surveys, one in the south, goes right up to the equator, called 6DF, very good, but this is in the north. There's been the Sloan survey, but this is, the initial Sloan survey was in the galactic north. This is in the galactic south. So this happens to fall in the part of the sky that's been least surveyed. And of course, we'd like to change that.
So what about the velocities of the galaxies out in the middle of the hole? I mean, I pictured the thing is, these guys sitting in the middle,
Yeah.
they don't know which way to go. They're
That's
just
true.
sitting there.
That's right. Yep, that, except that, of course, there's not much there almost by definition. But there are occasionally things, and we actually found something that is almost 9 megaparsecs up, right up here. It really was nice. And that's, we got HSD distance from tip of the giant branch and find it slowing down. Yeah.
Is it going fast or slow?
It's going a little faster than our model.
That was what you said.
Yeah, yeah. But it's not in the center. You'd have to go a lot farther up to get in the center, yeah. Yeah. Here and there.
So going back to your first slide, galactic coordinates, is that really then a projection of these velocities on the sky?
This one here,
No, all the way at the beginning of your talk, how do we interpret that in terms of these velocities?
yeah, well, I mean, okay, so this observed is actually only about 350 kilometers per second, because it happens that this is almost in the exact opposite direction. The rotation and the falling towards Andromeda are adding, so it's a funny thing.
240.
Yeah. And so all of the, so the initial map then is the sum of everything, you know, the sum of everything, the infall towards Virgo, everything else.
So if you subtract that, then what would you get?
So I, have to do all of that subtraction. The fact is that these motions here are, essentially doubling it, because while local group is going off that way, we're going this way towards Andromeda.
So these are like killer emotions then, right? That
Yeah.
you really want to remove to then see the larger scale.
Yeah, yeah. So, this is nature's idea of a vector addition for us all. This is vector addition.
More questions? So Brent, the one that I raised earlier, what about stuff outside the box, the, influences
Yeah.
from whatever else we're not seeing out there?
Okay. So then the thing there is the measurement people are making is bulk flow. And we have found then that on a scale of 15,000 kilometers per second, we still have a bulk flow of 100 kilometers per second or so. This is within the constraints of Lambda-CDM, but it's a little uncomfortable for Lambda-CDM, but it's still within those constraints. So the basic thing here is we do not have a fair sample of the universe. So we do not yet have an explanation that we cannot say that something at 0.1c is not a thing for interest. We need to go probably twice as far, 8 times the volume, to really be confident that either we have a fair sample or we don't really understand what's going on.
And what are your prospects for doing that?
Supernova. It's the only way. Yeah, we got to go on.
Bigger telescopes won't do the job?
No, not even. Bigger telescopes are not going to do this job. If John Tonry were here, his Atlas thing. His Atlas experiment, we should be picking up a couple thousand supernova within 10th velocity of light. This is the volume we want. And it's a small telescope, but you would pick up essentially every supernova in the available sky out to a 10th velocity of light. And so we get a couple of thousand supernova every year. Come back in a decade, you'd really have the sample to do this. I don't see any other way.
Wow. Other questions? Boy, everybody's worn out. Overwhelmed. Stunned. Yeah, that's very well. Okay, well, thank you very much. So you had Omega is a 0.55.
That's the big one. That's the big one. Yeah.
Big hole. And then I'm gonna say, okay, now what the hell?